in the last video, we set out to figure out the surface area of the walls of this weird looking building, where the ceiling of the walls was defined by the function f of xy is equal to x plus y squared. And then the base of this building, or the contour of its walls, was defined by the path where we have a circle of radius 2 along here. Then we go down along the y-axis, and then we take another left, and we go along the x-axis, and that was our building. And in the last video, we figured out this first wall's surface area. In fact, you can think of it, our original problem is we wanted to figure out the line integral along the closed path, so it was a closed line integral, along the closed path C of f of xy, and we're always multiplying f of xy times a little small distance of our path, ds. We're writing this in the most abstract way possible. And what we saw in the last video is the easiest way to do this is to break this up into multiple paths, or into multiple problems. So you can imagine this whole contour, this whole path we call C, but we could call this part that we figured out in the last video C1. This part we can call, make a pointer, C2. And then this point right here, C3. So we could redefine, or we can break up this line integral, this closed line integral, into 3 non-closed line integrals. This will be equal to the line integral along the path C1 of f of xy ds plus the line integral along C2 of f of xy ds plus the line integral, you might have guessed it, along C3 of f of xy ds. And in the last video, we got as far as figuring out this first part, this first curvy wall right here. Its surface area we figured out was 4 plus 2 pi. 4 plus 2 pi. Now we got to figure out the other two parts. So let's do C2. Let's do this line integral next. And in order to do it, we need to do another parametrization of x and y. It's going to be different than what we did for this part. We're no longer along this circle. We're just along the y-axis. So as long as we're there, x is definitely going to be equal to 0. So that's my parametrization. X is equal to 0. If we're along the y-axis, x is definitely equal to 0. And then y, you could say it starts off at y is equal to 2. Y is equal to 2. Maybe we'll say y is equal to 2 minus t. For t is between 0. T is greater than or equal to 0, less than or equal to 2. And that should work. When t is equal to 0, we're at this point right there. And then as t increases towards 2, we move down the y-axis until eventually when t is equal to 2, we're at that point right there. So that's our parametrization. And so let's evaluate this line. And actually, we can do our derivatives too if we like. What's the derivative? This we got right here. What's dx dt? Pretty straightforward. Derivative of 0 is 0. And dy dt is equal to the derivative of this is just minus 1, right? 2 minus t, derivative of minus t is just minus 1. And so let's just break it up. So we have this thing right here. So we have the integral along C2. But let's, instead of writing C2, I'll leave C2 there, but we'll say we're going from t is equal to 0 to 2 of f of xy. F of xy. So f of xy is this thing right here, is x plus y squared. And then times ds. And we know from the last several videos, ds can be rewritten as the square root of dx dt squared, so 0 squared, plus dy dt squared, so minus 1 squared is 1. All of that times dt. And obviously this is pretty nice. It gets very nice and clean. This is 0 plus 1 square root. This just becomes 1. And then what is x? X, if we write it in terms of our parametrization, is always going to be equal to 0. And then y squared is going to be 2 minus t squared. So this is going to be 2 minus t squared. So this whole crazy thing simplified to, we're going to go from t is equal to 0 to t is equal to 2. The x disappears in our parametrization. X just stays 0 regardless of what t is. Of y, and then you have y squared, but y is the same thing as 2 minus t. So 2 minus t squared. And then you have your dt sitting out there. This is pretty straightforward. I always find it easier to find when you're finding an antiderivative of this. Although you can do this in your head. I like to just actually multiply out this binomial. So this is going to be equal to the antiderivative from t is equal to 0 to t is equal to 2 of 4 minus 2 minus 4t plus t squared plus t squared, just like that, dt. And this is pretty straightforward. This is going to be the antiderivative of this is 4t minus 2t squared, right? When you take the derivative, 2 times minus 2 is minus 4t. And then you have plus 1/3 t to the third, right? These are just simple antiderivatives, and we need to evaluate it from 0 to 2. And so let's evaluate it at 2. 4 times 2 is 8. Let me pick a new color. 4 times 2 is 8 minus 2 times 2 squared. So 2 times 4, so minus 8 plus 1/3 times 2 to the third power. So 1/3 times 8. So these cancel out. We have 8 minus 8. And we just have 8/3. So this just becomes 8/3. And then we have to put a 0 in, minus 0 evaluated here. But this is just going to be 0. We have 4 times 0, 2 times 0. All of these are going to be 0. So minus 0. So just like that, we found our surface area of our second wall. This turned out being, this right here is 8/3. And now we have our last wall. And then we can just add them up. So we have our last wall. We're looking, so let's just, I'll do another parameterization. I want to have the graph there. Well, maybe I can paste it again. Edit. So there's the graph again. And now we're going to do our last wall. So our last wall is this one right here, which is, we could write it, this was C3. Let me switch colors here. So this is C. We're going to go along contour C3 of f of xy ds, which is the same thing as, let's do a parameterization. Along this curve, if we just say x is equal to t, very straightforward, for t is greater than or equal to 0, less than or equal to 2. And then this whole time that we're along the x-axis, y is going to be equal to 0. That's a pretty straightforward parameterization. So this is going to be equal to, we're going to go from t is equal to 0 to t is equal to 2, of f of xy, which is, I'll write in terms of x right now, x and y, x plus y squared, times ds. Now, what is dx? Well, let me write ds right here, times ds. That's what we're dealing with. Now, we know what ds is. ds is equal to the square root of dx dt squared plus dy dt squared times dt. We proved that in the first video, or we didn't rigorously prove it, but we got the sense of why this is true. And what's the derivative of x with respect to t? Well, it's just 1. So this is just going to be a 1. 1 squared, same thing. And the derivative of y with respect to t is 0. So this is a 0. 1 plus 0 is 1. Square root of 1 is 1. So this thing just becomes dt. ds is going to be equal to dt in this case. So this just becomes a dt. And then our x is going to be equal to a t. That's our definition of our parameterization. And y is 0, so we can ignore it. So this was a super simple integral. So this simplified down to, we're going to go from 0 to 2 of t dt, which is equal to, the antiderivative of t is just 1/2 t squared. And we're going to go 0 to 2, which is equal to 1/2 times 2 squared. 2 squared is 4, times 1/2 is 2. And then minus 1/2 times 0 squared, minus 0. So this third wall's area right there is just 2. Pretty straightforward. So that right there, the area there is just 2. And so to answer our question, what was this line integral evaluated over this closed path of f of xy? Well, we just add up these numbers. We have 4 plus 2 pi plus 8/3 plus 2. Well, what is this? 8/3 is the same thing as 2 2/3. So we have 4 plus 2 2/3 is 6 2/3, plus another 2 is 8 2/3. So this whole thing becomes 8 2/3, if you write it as a mixed number, plus 2 pi. And we're done. Now we can start trying to do line integrals with vector-valued functions.